In this video, we're briefly going to look at the law of the conservation of mass. Sometimes when I'm teaching it, I call it first law of chemistry. And basically speaking, it is in a chemical reaction, mass can neither be created nor destroyed. I sometimes tell students chemistry is not magic. It's impossible just to magic up new matter or indeed destroy matter that you started with. Anyway, for a definition, what is the law of conservation of mass? This states that in a closed system, that's quite important, we're going to come to that definition closed system in a moment, that matter, the mass, that is neither created or destroyed. Now there's plenty of ways we can define the laws of conservation of mass, but essentially that's a decent one to be going on with. Now we've got three systems down here, and it's interesting whether this is not necessarily a closed system. So what we're asked here in each of these three experiments, whether the mass goes up, down, or stays the same. So we've got three flasks, three different reactions on a top pan balance. And coincidentally, the top pan balance in each one says 132.38. It's because when I did this, I copied and pasted this across and just changed the reactants. I possibly should have changed the mass slightly, but that's no relevance, that coincidence. Okay, so let's deal with this middle system first. We've got copper sulfate aqueous. That's the blue copper sulfate solution that's in here. It's coloured grey, but it's a liquid. So that's the copper sulfate, that's the solution. And we're adding zinc to it, and there are zinc granules. Zinc is grey. Now we're getting a displacement reaction going on here. The zinc is more reactive than the copper, so it will take the sulfate. So our products are zinc sulfate aqueous and copper solid. Okay, so this is a closed system. We have a cotton wool plug on the top to make sure no liquid can escape or nothing can enter really, but air can get in and out if it needs to. Not that it needs to in this reaction. So there will be no change in mass here. The law of conservation of mass absolutely applies in a closed system, and to all intents and purposes in this reaction this is a closed system. All the copper atoms on the left are going to be on the right-hand side after they've reacted, same with the sulfate ions, and same with the zinc. Okay, they are going to, none of those are going to be destroyed or indeed created in the reaction. So no change. No matter is gained or lost from the flask. Okay, so we've done the easy example first. Often when I give students this definition and I ask them this question down here, every student says no change, no change, no change. And of course, sometimes life is a little bit more complex than the definition. If these were closed systems, it would be no change, no change, no change, but they're not. Okay, this example here now. We've got calcium carbonate, that's a solid limestone down the bottom there, the chips. We react it with hydrochloric acid, that's the solution surrounding the calcium carbonate. Now this is going to produce calcium chloride, a salt which will stay in solution, water which will join the calcium chloride in solution, and also this one, carbon dioxide gas. And the state symbol there is quite important. This will fizz and bubble. Okay, so this is giving off a gas. Now this is a cotton wool plug. Okay, as it bubbles away, some bits of the liquid will bubble up as well, in the same way when you drink a can of Coke, you sometimes feel the Coke hitting your lips or your cheek as the bubbles burst on the surface. Well, that cotton wool plug is to stop any of that liquid escaping. Okay, that's important. Having said that, the cotton wool plug will let the carbon dioxide out. The carbon dioxide will go out. So out of here will go carbon dioxide. Okay, now carbon dioxide is matter. So matter is being lost from this flask. Therefore, the mass will decrease. Answer, and the reason, the reaction is giving off CO2 gas. Okay, and because of that, this reading will be going down, 132.2, 132.1, 131 as time goes by. this example here. In this example, we have got potassium, just potassium. Potassium is an incredibly reactive metal, okay, and it's going to react, in this example, with oxygen from the air. So the air is 20% oxygen, 80% nitrogen. Okay, so we've got oxygen all around us here, and the oxygen is going in this time, as this potassium metal tarnishes and reacts with the oxygen in the air. The product of that reaction is potassium oxide. So the mass of this one is not going to stay the same because oxygen is coming in. It's not going to decrease because oxygen is being added this time to the flask. The potassium oxide will weigh more than the potassium. Okay, so the mass of this one will increase. Okay, oxygen from the atmosphere is being added to the potassium in the flask. Okay, so we've got three different scenarios. Okay, this one decreases because it gives off a gas. This one stays the same because nothing goes in or goes out. And this one increases because a gas joins the potassium on the balance. And that's the law of the conservation of mass.